Hello, quick video on integration by parts. In differentiation, we spent a lot of time working on product rule, which allowed us to differentiate the product of two functions. And in integration by parts, we're going to go the reverse way through the process. And therefore that will allow us to integrate products here like x cos x, or x squared sine x, or x cubed e to the x, or x to the log of x. And this is known as integration by parts because we're going to break it into our two parts and then we're going to deal with it. Let me give you a quick explanation of why this works and then we'll do an example. Here's our product rule here. And the differential of ux equals u dv by dx plus v du by dx. Yeah, if we just rearrange that, because I would like to make this a second term here, this on the right, the first term on the right hand side here, I'm going to make that the subject. Yeah, so therefore just rearranging u dv by dx is therefore going to equal the differential of uv minus, I subtract v du by dx. Yeah, so if I start with that, we're comfortable, that's just to rearrange. Then on my next step is just to take this equation I've got and then integrate it. Yeah, so I'm going to integrate each of these terms like that. Yeah, and if the basic's true, then the integral must be true. So there we have it. So the integral of u dv by dx is going to be equal to this integral, which is the integral of a differential, and then they take away the v du by dx term. Yeah. Now this middle term here, if we take a function uv and we differentiate it and then we integrate it again, we're going to come back to uv. So effectively we've integrated that part. And then our second term, well, that's going to be our v du by dx. And that's basically our equation that we're going to use. And when are we going to use it? Well, in situations where we may not be able to integrate u dv by dx, but we may actually be able to integrate v du by dx. So let's look at an example, shall we? Okay, here we are. Let's integrate x cos of x. So the first thing we need to decide, we're going to equate it to this term here on the left hand side, and we're going to work out the terms on the right hand side. So we need to decide which is u and which is dv by dx. Well, if we could get rid of this u by differentiating it, it would go down, that x rather, it would go down to 1, wouldn't it? So that looks quite good to make that equal to u, and if we make that equal to u so it goes away, and we differentiate it in a minute over here on the right hand side, that means that our dv by dx must be cos theta. And we can probably integrate that, can't we? Because we know how to integrate and differentiate trig ratios. So therefore u equals x and dv by dx equals cos of theta. Now, as we did in the product rule, I'd recommend that you set it out in a standard format, and here's my little square again. So on the left hand side, if u equals x, then it's easy to see that du by dx will equal 1. Yeah. And on the right hand side, if dv by dx equals cos of x, then we integrate that and we know that v will equal the sine of x. Now we've got all these terms, we can substitute them into the equation. So here we go, there's our standard by parts equation here. So on the left hand side, that's what we started with. So in the middle we have uv, so u is x and v is sine of x from what we've worked out above. And then in the integral we have v, which is sine of x, times du by dx, which we know from above is 1. So we've now got a straightforward integral here, haven't we? We've effectively integrated the middle term already, and here's an integral we can do because sine x times 1 is just sine of x, and if the integral sine x we know is minus cos of x, don't we? So therefore if we integrate this term here, the minus sine of x will become plus cos of x. So there we found that whilst we couldn't integrate x cos of x, we could, using by parts, integrate effectively sine x times 1, and therefore we got our answer. So in general terms, our first key learning point is if we see a product like this function that we're trying to integrate, we're going to be interested in making our x value u, because then as we differentiate it to get our u by dx, it's going to come to 1, isn't it? And we're now going to extend this a bit by starting to think about the fact that if we had an x squared or an x cubed, what we're going to do there. So let's have a look at, as our second example, let's integrate x squared cos of x. And as we said earlier, we want to differentiate our x squared away, so therefore we make u equals x squared, and as we had before, dv by dx is going to be cos of x. If we make up our little table, our u of x squared means that du by dx equals 2 of x, and we just differentiated that. And as we saw before, if dv by dx is cos of x, then v equals sine of x. So let's substitute those into our standard by parts equation there in red, and therefore our middle term is going to be our u, which is x squared, and our v, which is sine of x. And then our integral on the right hand term is going to be our v times the differential of u, which was x squared, so we end up with 2x. There we are. So we've integrated this term here, and we could carry on and do that, but we still can't integrate this term here because we've got an x sine of x inside that integral, haven't we? So what's the solution to that? Well, we're going to repeat our by parts process. I'm going to do this in a different colour so we can see it. So in this case, we're going to make our, again, like we did before, we want to differentiate our x away. So let's make u equal to 2x, and let's make dv by dx equals sine of x. Therefore, in our little table, du by dx is going to be 2, and v is going to be minus cos of x. So we can now substitute, we can now replace this final term, the right-hand term, with this product rule. So, so in the by parts rather. So let's do that. So if we substitute that in, I've done that in this orange colour, we've got the terms we had before, and in place of our final term, we've got our new u and v values, and here in the integral, we've got our v value and our du by dx, which is just going to be 2. So if we do a bit of tidying up, we've got our x squared sine x term we created from our first by parts. We've got our second by parts uv there, two minus signs to multiples of minus, so that's going to become a plus 2x cos x, and then our integral, our final term here. Now our 2x just turned into an x here, hasn't it? So we've effectively got two lots of cos of x, and we had three minus signs here, so minus times a minus 1 is all going to be a minus 1. There we are. And now we can integrate that, can't we? Because we know how to integrate cos of x, and that would give us minus, that would give us sine of x, wouldn't it? Therefore, now we've got three parts to our solution to the integral of x squared cos of x. There we had our first uv, there x squared sine of x. Here's our second uv term, and 2x cos x, and our final integral now, which we could do having got rid of our x squared by double differentiating it, we ended up at 2 sine x. So there we are. Key learning points then are, in these sorts of cases, every time we see an x squared or x cubed or some polynomial made up of that, we're going to make that our u, and then our dv by dx is going to be our cos, or our e to the x, whatever else we've got here. And if it doesn't go away the first time, which it won't here, if we had an x squared, it would become an x in the third term on the right hand end, or an x cubed, it would become an x squared. We just double differentiate or triple differentiate until it all comes down to unit values. Yeah. Now, there's only one exception to what we've just done, and that's if the other term inside our bracket is a log. So here we've got x log x. Now our problem is we don't know how to integrate log of x, do we? Because we'd like to make, we would start by thinking, oh, we'll make u equal to x. which means that log of x has got to become dv by dx, and we don't know how to integrate a log of x. So we can't do that. We do know how to differentiate log of x. So if you see one of these with a log of x, you've got to make log of x equal to u, which means that dv by dx is going to have to be the x value. And now if we go through as we've done before, create our little table. If u equals log of x, then du by dx equals 1 over x. And if dv by dx is x, then v itself is going to be x squared over 2, isn't it? Now, if we substitute those into our by parts equation, then we get our u value here and our v value. So log x times x squared over 2 multiplied by, and inside our integral we get our v value here, x squared over 2, and our differential of u, which is 1 over x. Now the good thing about this is if we've got a function of x as being our v value, then of course our x's are going to cancel out here, aren't they? So here we've got an integral that we can do, because effectively our final integral is now the integral of our half of x dx. You know, we can take the x out, there's the half out the front, and therefore what have we got? We've got, yeah, x squared over 2 would be, and when we've taken that 2 out, divide by 2 out the front, so we've got a quarter, haven't we? So the integral of x log of x dx is going to be our log x times x squared over 2, that's our uv term. And here our second integral here, where we got our log of x effectively got turned into a 1 over x, did some cancellation integration. So there we are. That one works. If you see those ones with a log of x, you've got to go a different route. So in summary, we use integration by parts to find the integral of a product of a function, and particularly where we don't know how to integrate this term, this original integral, so we rearrange it in parts to be a new uv, take away the v du term. So we can do that for all of these cases here, the integral of x cos x, or the integral of x squared sine x, or the integral of x cubed e to the x. And in all of these cases, we make our x, or our x squared, or our x cubed equal to u, yeah? And then we might have to double differentiate or treble, so double parts or treble parts this, repeating the parts process 1, 2, 3, 4 times until we get rid of our x cubed, or x for 4. But it will go away, it will come down to a basic integral in the end at the right hand end. The only thing we need to watch out for is this one exception where we've got an x times a log of x, and if we see a log of x, then we've got to make that the u, so we can differentiate that to 1 over x, and then things will start cancelling out after that. So there we are. I hope that's of use.